The title of this paper is Deep Learning for Identifying Malicious Firmware. Thank you to the conference for inviting us. And we want to explain, we want to motivate why this problem is important and what is the Internet of Things firmware challenge. And then we're going to explore some of the novel techniques that can be applied to detect malware when it's implanted in the Internet of Things firmware updates. We'll outline the method and approach, how we prepare the data set, where we got it, the modeling parameters that we use to determine malware. And finally, we're going to do some data exploration with a combination of statistical machine learning, so things like decision trees, and more obvious ways to interpret the results. And then finally, we're going to try and push the envelope of deep neural networks with transfer learning, which is a familiar and successful way of solving a lot of image classification problems. So the motivation for this problem, of course, is the Internet of Things is exploding. About 500 billion Internet of Things devices, everything from the phone to the thermostat to industrial control systems. If you think about it, that's about 6 devices per person on the planet. And there's sort of 2 categories, obviously the personal thermostats, appliances, personal assistants, and of course, on a much bigger scale, the industrial, which is control units, SCADA devices, dams, utilities, pipelines, and stadiums. So when you think about how you want to install Internet of Things, as opposed to, say, managing an enterprise network of computers, there's a big reward for convenient installation. Typically, these are not trained people. You buy a new phone and you immediately want it to connect to networks. And so there are some big challenges to protecting these devices, particularly when you think about all the important stuff in our physical parts of our lives that are attached to it. So typically, you know, a device will come with automated attachment to the network, so-called promiscuous modes. They also typically don't have an interface to provide good password management, so weak or no passwords, things like admin or root. And often for debugging purposes, the serial port is left wide open. And that goes all the way through to installation. And on the right side, you see just some typical examples people cite that are potentially problematic if the Internet of Things is not secured. Everything from SCADA devices in nuclear plants to this is a picture from the 2018 Olympics in South Korea, in which the printers were disabled largely in what was thought to be a nation state attack on Korean Olympics. They could not issue the gate tickets from the printers at the opening ceremonies. So the proposed solution we wanted to investigate is, how would you map what is an abstract piece of software? Could be just an ordinary executable, it could be a dynamic link library, a DLL, or it could be an update to your phone. And so we want to map firmware into the abstract of the image space. And we'll discuss why that might or might not make much sense here. But we want to solve this as a classification problem in image space and leverage as much of the deep learning advances that have happened on the image side since 2012. So in sort of picture format, what you see over here in the bottom, and I'll explain this in a little more detail later, but basically this is a byte map moved into image space. So if you think of taking the first 1024, so this is a 32 by 32 grayscale image, and we're going to map the abstract bytes in the executable, just read that header, and we're going to convert it to decimal, so 0 to 15, and then we're going to, on a 16-bit integer, and then we're going to scale that to 0 to 255 in color space, or sorry, in grayscale space. So what you end up doing is getting a very, I like to call it a fingerprint of that executable. And then we're going to look at a lot of these and try and find similarities or dissimilarities between benign versions of this image and malicious versions of this image. So in a classic classification problem, this is the kind of two samples. We're going to have 4 different classes, I'll explain. But you basically want to find this line that divides the 2 classes. So this could be malicious and this could be benign. And if you follow the development in deep learning, they typically like to not do a lot of initial feature extraction. In other words, I'm not going to look for edges. I'm not going to look for color boundaries. I'm really just going to look at raw pixels. And by extending the depth of this neural network, I will eventually come to a decision. Is it malicious or benign based on the image alone? So that's kind of the program that we're going to investigate in the talk. So first of all, to introduce this, we're going to use a thing called ELF, which is an executable link format. It's widely used in really throughout the Linux world, but also in the Internet of Things, and it's basically an executable. So I list some of the places you would find an ELF file at the OS level, Android, Linux, in a number of games from PlayStation to Wii. There are a number of phone operating systems, Samsung, Ericsson, Nokia. And finally, you get down to the real heart of Internet of Things, which is microcontrollers made by Texas Instruments or Atmel. And as I described, this is the structure of that executable. The first 1024 bytes can pretty much describe this header of the executable, has a text piece, an introductory data piece, and a more extended data slice. And then you get to other parts of the executable. This basically loads it into the operating system. And so, as I said, we're going to take 1024. There's some reasons for that, based both on previous work, but also this scale 32 by 32 is a convenient, it's called stride length. So it forms an even number for which you can do deep learning on. So this is a number of, this is kind of the abstract class problem. So here are 4 examples of those fingerprints of malware for Internet of Things updates. And here are 4 of what's called hackware. And these are a subversion of malware, but basically it can disable it without necessarily exporting data or linking it to other parts of the network. And in fact, we're going to add 2 more classes. We want binary, and then we also want an unknown class, meaning I have no decision to make. So why would you want to do what is essentially already an abstract problem in bytes? Why would you want to do that in images? Well, really the motivation in April of 2020, this paper was produced by Intel and Microsoft, and it's a project they call Stamina, which is scalable deep learning for malware classification. Obviously, Intel and Microsoft, it's mainly at the operating system level and not the Internet of Things, but they're looking for viruses. And many people are aware that virus detection based on either behavior of the virus, for example, that executable shouldn't be running in that place on my operating system, or the actual hash, which means the byte by byte signature of the file. Both of those are easily hacked because I can change 1 byte and suddenly the hash changes, and my signature detection, whether it's McAfee or Kaspersky, whatever my virus detector suddenly gets slipped. So that's the first thing that sort of piqued our interest. And then we found in 2021, there's the GitHub, which is basically 10 to 40,000 Internet of Things ELF files. So the executable link format, and these are in bytes. And so the thought was, let's combine these 2. Let's take the initial idea from Intel and Microsoft and see if we can apply it to Internet of Things. And the final motivation is you have to really appreciate how these sort of thumbnail grayscale images have exploded in the machine learning world. Most everyone is familiar with the MNIST data set. It's really the most popular image benchmark. And in various forms, it can be recognizing digits 0 to handwritten digits 0 to 9 in grayscale. So this looks very similar to our images of executable malware. But it also has branched. People have said, you know, if they're going to solve that handwriting recognition, and typically it's 99% with the deep learning method, I can move it to other things, such as I can recognize different kinds of clothes, and that's called fashion MNIST. Or I can recognize medical images, and that's called a medical NIST. And all the way down to satellite imagery. So this has really become the heart. So in 3 pieces, this was the kernel of the idea. This was a data set that we could build in image space, and this is the productivity of using images for deep learning. And we're going to do deep learning in a very productive way, a very efficient way. A very popular architecture is called Mobilenet V2. It was originally described by Google. And it has a couple features that are a little bit unique. For those familiar with deep learning, it's somewhat traditional neural networks, but with a lot of intermediate layers and a lot of unique operations. Some of the unique operations, Mobilenet is really capable of running on an IoT device. It's that small. So typically you can make a 2 megabyte or smaller neural network that will work on the classifier problem to great efficiency. So some of its features that were attractive to us, this is kind of the schematic, but it has a sort of repetitive building block. So it has deep layers, and the intermediate layers you can stack like bricks or Lego blocks. It also addresses directly a problem that many people encounter in deep learning, that is, if you train it on many images, eventually you no longer improve your solution. And so this is called the vanishing gradient problem. So if you're hill climbing, you eventually plateau. And people have figured out that you can use the residual and not the gradient, and you can sort of restore the learning capability. And we'll show some learning curves that will make that clear. And finally, it has this ability to recall previous layers. So it has a kind of shortcut or shunt that takes you from one layer all the way back to previous layers. And the basic operation of convolution is I'm just going to do weighted sums. So if you imagine, there's different ways to make these blocks, but I'm going to take a pixel and essentially take the average of the pixels around it in different 3 by 3, 5 by 5, and you can build up a hierarchy of recognizable features. And so the way you do this is, obviously there's no real program to write here. You're just essentially feeding in raw pixels, pixel 1 to pixel 2024. And that will go into these layers, and then you can do different tasks with it. And as I say, really the attraction here is it's both fast, accurate, and modular. So as I said, we want to look at this data set, which are the binary executables. And it's very interesting to look at this as a human would and then appreciate the power of the machine view of this. But this is benignware. So this could be an update to your iPhone or Android device. This could be a thermostat, and this could be issued by the manufacturer. And these dots represent different binary codes translated to pixels. To contrast that, we want to look for dissimilarities between benignware or good software and bad software. So this clearly has some patterns here. For example, this could be 800 to 900 bytes into the file. You see a lot of white spaces. You don't see them here. Finally, this is hackware, which is the subset of malware, and we want to distinguish this class. And then we have a series of blanks, which are basically grayscale solids, and we'll call those unknown. So we have about 3,000 examples from the GitHub that we translated into images. And so 3,000 good pieces of software as images, 714 malware, and about 100 examples of hackware. Unknown was basically a balance. So we're going to solve it in two methods. We're going to use a small subset. So this is what's known as an imbalanced data set. And if you run this as is without trying to balance it, the neural network often will converge or predict that's benign, simply because it's seen more examples. And so you have two ways. You can look at this as 100. You can subset the overrepresented class, or you can oversample the underrepresented class. And we're going to solve both those problems and compare them. So this is kind of the summary of how we created those images. And I've mentioned it's a 32 by 32 grayscale. We converted to decimals between integer values between 0 and 15 for each byte. And then we expand that to 0 to 255 to make a grayscale. And this is similar to the technique used by the Stamina project. And then it's important to know that these really are just bytes. And that finally, each one of these has its own file naming convention. So if you think about the way you compile an executable, it has its own architecture like x86. It has its own bit, which is 64-bit, endianness and the system and what's the compiler. And so this is probably 18 subcategories that you could eventually imagine you might want to pull out of this image if you do it as a multi-class, a huge class problem. So first question you want to ask of this is, what are the important parts of this image? And in bytes or pixels. And so this is an example piece of software. You can think of it as a fingerprint. And if you look at your fingerprint, there's spiral techniques to take apart a fingerprint that humans use. And that typically focuses on the center of your thumb. And as you go out, perhaps those peripheral does not make as much difference. In this case, we use a technique which is common to something called random forest, which I'll describe in pictorial means, but this is basically the importance list. So these are the top 10. So if out of over 1,000 pixels, these are your top 10 contributions to distinguishing benign from hack to malware. And we've sorted them by malware, and you can see pixel 265, which could be this one, pixel 633, which could be somewhere in the middle, on down here to pixel 653, which is also somewhere here. And so if you want to imagine how do you determine the importance of a pixel, you essentially knock it out of the decision tree. And if you're no longer able to distinguish these classes as well as with it, you assume that must be a determining factor. So in a medical context, if I say, what's the risk of heart attack? And I have age, gender, weight, and I take out age, and I no longer can evaluate the risk of heart attack, then you can essentially say age is an important contributing factor. And that's what we do here, except in the abstract of pixel space. So oftentimes, in addition to accuracy, if you were doing forensic analysis, for instance, on this piece of software, this would tell you, you know what, I'm going to look at pixel 265 and see if there's something there which could be giving me a clue about the way the hacker is compiling that software. So I mentioned before that this Mobilenet V2, we're training it using transfer learning. That's a technique where you essentially have trained it on an entirely different class of objects. Could be dogs, could be cats, could be people, and you slice off the last layer of that deep neural network, and then you give it a new class. So what that often does is, if it's a massive internet scale database, say millions of examples and not the thousands here, you've already built up the recognition of hierarchical features. So for example, circles, squares, eyes, nose, which may not be relevant to this, but you have begun a way to filter different parts of the image to represent the neighborhood of its surrounding area. So that tends to be very efficient and get higher accuracy. And so these are our experiments. In this case, we're looking at loss, which means we're getting closer and closer to the right answer. And these are the epochs, so the number of times we cycle the images back through the neural network. An important feature of training a neural network, obviously, is feedback. And you can particularly tell the orange here is the test, and the purple, the blue here is the training. And the fact that these typically follow the same pattern means we're not over-learning. If you're memorizing the data, the training data set, you'll typically see the orange, the test set, suddenly does not get as good a value. So that's a clue that we're onto something here. And you can compare it also to typically what I show here is a good learning rate. This is plateaued too early. This is still got something to learn, so it's not learning fast enough. And this one essentially has taken off, meaning we're disrupting the learning prematurely. So finally, this is the sort of obligatory table of results. And these are our classes: benign, mal, hackware, and unknown. And we're first using the large files, meaning more overrepresented classes of malware and hackware. And clearly, we're anywhere from 98 to 100% accurate on these 4 classes in the large sample. And we wanted to find out how many samples does it really take to get a benchmark, like 90, 95% accurate. And so if you cut that down to about 100 samples, you begin to see some decay, but clearly unknown here, which if you recall is just those grayscale blanks. That can typically is easily recognizable from the other 3, which a human perhaps would have trouble recognizing. So we wanted to explore further. That's a black box model. It's you have to kind of just trust the machine to say, I know that that's malware. It's similar to a signature hash. In that sense, a fingerprint of the file. And there's not a lot of more information you can extract out of it. But people like to do what you could call explainable AI. And typically that is a throwback to a less accurate but statistically understandable technique. So the first version of that is a single decision tree, very popular in credit scores and medical fields. And so we basically build a single decision tree, and that's what it looks like. And we're making decisions based on pixel values. So if you recall, pixels can map from low to high, 0 to 255 on a grayscale. And this says, if this pixel 265, which could be here, is very dark, then we'll go down this branch, and eventually it will become benign where if that pixel is low. If we go here and it's much brighter, then we go to we go down this branch of decisions. And at the end of the day, you can see through about 6 or 7 forks, we've divided the entire configuration here into our 4 classes. Now, the real value of this is I can convince you that these are the critical pixels. I also, if I'm a hacker and I know that this is your method of detecting me, I can really fiddle with as few as 6 or 7 pixels or bytes in my file. And so now I've mapped the hash problem to something that's much more potentially vulnerable to attack because I've identified the 7 or 8 determining factors of this executable. But that gives you insight into explainable AI. The extension, the challenge with a single decision tree, of course, is what I was describing of a hacker can say, you know what, if you only have 6 or 7 pixels, I can modify my file and essentially confuse this single decision tree. So the natural extension is to go to many decision trees or ensemble them. And the way you do this could be anywhere from 50 to 500 of these individual decision trees, but we're not going to reveal the entire data set either in pixels or the entire image to each one of the decision trees. So essentially, these are all getting a different view in. If you view it as a chessboard, you may be only looking at a quarter of the chessboard and trying to infer the action outside of your narrow point of view. Turns out this technique is pretty powerful, and you're trying to balance the trade-off between memorizing and generalizing. Also trying to make this less brittle to attack. So this is kind of a nice graphic of the way that works. So we built anywhere from 50 to 500 voting decision trees. It looks like a single decision tree. This is actually one of 500. But if you think of this in pixel space, now I have a lot more pixels that I have a more robust classifier. So if you start here and you know I'm going to decide way out here on the periphery of this circular tree, this is benignware, and I've gotten there through this method. This is malware, and I've gotten here through these decisions in pure pixel space. And each one of these pixels, again, maps to our executable. One of the really interesting parts of this is these ensembles have the potential to do much better, and we think this is an area for future exploration, to generalize much better for zero-day malware. So many of the nation states will pay a lot of money, for example, for an iPhone attack that is not, has previously never been seen. And the thought is if you put this as a screener, for example, on the Apple Store or the App Store, this could be an interesting way to generalize outside of your original training data. So in summary or conclusion, this is a novel technique. In many ways, it's not intuitive, but if you're familiar with kind of the success story of image classifiers and the number of ways people have used it to build powerful machine learning algorithms, we think this is a general way, for example, to look at malware or network intrusions. And we've even done it for tabular data sets. So for example, forget about this as an executable and just say these are columns and rows of your data set. You can map it to pixels and scale it and learn from it. An important part of doing this successfully is to recognize imbalanced data sets. Obviously, if you're looking at thousands of pieces of software, 99.9% of those are going to be normal cases or benign. And as a consequence, be aware that you need to balance or either undersample or oversample normal to recognize abnormal. So we basically solved this problem multiple times for 100 to 3,000 images per class. Typically, 100 is kind of a minimum in the image space, particularly if you're applying all that you know in transfer learning from other data sets. So future work, we think if you Google MNIST data set on Google Scholar, you'll see more than 55,000 research papers since 2000, when it was really sort of became introduced as a deep learning or a machine learning challenge. Of those 55,000, 8,000 have been published just this year. So MNIST people often say, for example, what fruit flies are to biology, MNIST is to machine learning, meaning if I'm going to go out to test a theory, it needs to work on MNIST before I take it to more challenging problems. The beauty of what this approach offers is we can inherit all of the techniques, all that people have learned about this data set and apply it to a new frontier in Internet of Things malware. And we also, in conclusion, have applied a multi-tiered machine learning approach. Clearly, you want the most accurate. You can get 98 to 100% on a large data set in this image, which is very promising and very challenging for other approaches. But you can also use traditional tree-based methods and construct very, very small classifiers. So if you think about that initial decision tree that had 7 pixels, you could write that in any language using if-then statements and use it as an initial screen for whether these ELF binaries are useful for firmware updates. For future work, I would refer you to these 2 links. The data set that we used is available on Kaggle, which is a data competition. Just look for IoT firmware image classification and you can download this data set and try it. Also, a tip of our hat to this GitHub, in which they gave the raw executables, these ELF binaries, which we converted to image space and then began building models. We think this combination can be fruitful for other workers. And with that, I'll open it up to any questions. Thank you.